Okay, so this is the first video for section 9.4, where we're going to talk about what we call the simple linear model. So what we've done so far, 9.1 through 9.3, is given a data set, x1, y1 up through xn, yn, we figured out this linear regression, this line of best fit for that data set, okay? So in section 9.4, we asked the question, well, how does that linear regression model for a given data set, how does it compare with the linear model for the entire population that the data set came from? So you can imagine, given a population, I can grab 50, 1,000, 10 billion different data sets. And for each of these different data sets, I could make a slightly different linear model, okay? But you could think, well, there's some platonic ideal of a linear model that best fits the entire population. That's what we're going to be trying to calculate in this section, all right? And what we're going to eventually come up with is what our linear model will look like is it's going to be for the expected value of the y value, right? Not the actual y value, but just what we would expect that y value to be given the x value. So the expected value of y sub I will be an alpha plus a beta times the x sub I, right? So that's what we're eventually going to come up with. And we're going to ask ourselves, well, how well do these A's and B's tell us? What do they tell us about alphas and betas, right? Okay, and what we're going to look for is we're going to look for some significant tests, significance tests, like how significant is that be in terms of the alpha and the beta, and what are the confidence intervals for the alphas and the betas, right? Same things we've looked at before. All right. Well, and there's two methods we're going to do it. In section 9.4, this section, we're going to look at sort of a mathematical way, a formulaic or theory-based way. And the next section, we'll figure out another way of coming up with significance tests and confidence intervals using resampling via bootstrapping. Okay, so why don't you pause, copy this bad boy down, and then press play. All right, so we're trying to figure out this alpha and this beta, this population-wide slope and intercept for a linear model for a population, okay? And we're doing it based on theory, okay? So for this theory, we have to make certain assumptions, or our data has to fit certain assumptions for it to work well. So here are some of the assumptions. And by the way, we call this alpha plus beta xi the simple linear model. So here are our assumptions. I'm going to start with my data set. The x values are fixed and the y values are random, and they're independent of the other y values. So that's one assumption. Y1 is independent of y2, which is independent of y3, et cetera, okay? The next assumption, the distribution of the y value given x is going to be normal, all right? And for each x sub I, we might have a different mean, but the variance will always be constant, sigma squared, okay? So that's the variance of the y sub i's are going to be constant variance. Mu sub I is going to be expected value of y sub I, and that's what we're hoping to fit with this simple linear model, alpha plus beta times xi, okay? All right, so next assumption, the residuals. So the true y value is y sub I, and there's the expected y value, which is what our simple linear model will be telling us. The difference between them is our error, our residual, okay? We also need to have that the residuals are independent of each other. The residuals have constant variance, and that the residuals are normally distributed, okay? So these are the assumptions for the simple linear model. Some of these assumptions are pretty important, some of them aren't. So for example, the important ones are this guy. The expected value of y sub I follows a linear model. That's a huge assumption. And that the residuals are independent of each other. That's a pretty big assumption as well, okay? The others are not as major. All right, so here's the final panel for this video, okay? So why don't you pause, copy it down, and then press play. All right, so if we have all the assumptions on the previous panel for this data set, then we've got some great news, some reassuring news, let's say. If I figure out the maximum likelihood estimators of alpha, beta, and sigma squared, turns out they're kind of familiar. The maximum likelihood estimator of beta, which we'll call beta hat, is given by this expression right here, which should look very familiar to you. And the maximum likelihood estimator of alpha, the intercept, is given by the average of the mean of the y's minus beta hat times the mean of the x's, and that should look pretty familiar to you as well. And the maximum likelihood estimator of sigma squared, the variance of the y's given an x, is given by this quantity here, which might not look quite as familiar to you, but it should. That's well, that's not too far out of line with what we've seen before. So here's the good news. The maximum likelihood alpha estimators for alpha and beta are exactly in agreement with how we calculated A and B given a data set from section 9.3. Cool. All right. Some other important facts that are going to help us assign some distributions to these objects is that the estimator for sigma squared and for beta and the mean of y are all mutually independent of each other. And this quantity, n times sigma squared hat over sigma squared, has a chi-square distribution with n minus 2 degrees of freedom. Okay. Why n minus 2? Well, roughly speaking, the alpha and the beta occupy 2 of the slots. Okay. All right. Well, there's one small problem with sigma squared hat, the estimator for sigma squared. It's biased. All right. But we can fix it. So if I define s squared to be n over n minus 2 times sigma squared hat, the estimator sigma squared, that simplifies to this quantity. It turns out that s squared is an unbiased estimator of sigma squared. And I like unbiased estimators, so we're going to stick with that one. We call s squared either the residual standard error or the residual standard deviation. Okay. So the simple linear model is agreeing with the linear regression model for a given data set, and it's got some nice properties, right? So that's the good news.